let's say this is memory. Okay, and this is shared region. S1, right? This is another shared region, S2, and so on, right? And so there are multiple threads that are accessing these shared regions, right? And what we're talking about last time was that if multiple threads access the same shared region simultaneously, then there are problems. And so what we did was we said, let's, the programmer should allocate new shared variables, let's say L1 and L2, right? And make sure that whenever this is touched, L2 is held, right? And similarly, whenever this is touched, L1 is held, right? So L1 and L2 have acquire and release functionality, right? And so the programmer must make sure that whenever one thread is touching shared region S1, it is holding L1. Similarly, the programmer should ensure that whenever it is touching S2, it should hold L2, and so on, right? So the choice of how many locks to have is completely programmer dependent. The programmer could choose to use the same lock for both regions, right? So instead of having L1 and L2, he could have one L, which is protecting both S1 and S2. Or he could have multiple locks. So that's coarse-grained versus fine-grained. Also, if there is one operation that involves both S1 and S2, then he should a priori, so let's say there was one operation which said move some data from S2 to S1, right? In that case, he should hold both the locks L1 and L2 before doing that operation. Okay. So for example, if there was some operation which said move from S1 to S2, then the way I will write the code is I'll acquire both the locks L1 and L2, then do the operation, and then I'll release both the locks, right? So that's a better way than let's say I just acquire L1, then read data from S1, then release L1, then acquire L2. So we saw last time that there can be problems with that. So the safest thing to do is to, if there's an operation which involves multiple shared regions, just acquire all the locks first, do your operation which does all the shared regions, and then release all the locks. This basically ensures that nobody else can touch those regions while you were operating on those regions. Okay. And you also have to be sure that all operations that can potentially access this shared region always take the corresponding lock, right? So it should not be that so whenever you are touching shared region S1, you should always be holding L1. Holding L2 is not going to help, right? So it should not be that one thread is holding L1 and another thread is holding L2 and both are accessing S1. That's useless, right? They should be holding the same lock to be able to access the same location. Okay, right? So that was that was basically what we discussed last time. And so we saw one example. Let's say so we saw many examples. So for example, the one was we said insert into a list some data, right? So you recall that I had an example where I had said let there be a function called insert list, and this list was shared, right? And I said, okay, one way to do this is basically acquire, have a lock per list. So per list lock. And so you just say acquire list.lock and do the operation and say release list.lock. In this case, the shared region was only one, the list. And so only one lock for every shared region was required. So basically, if I were to look at memory, so let's say if I were to draw a picture like this, there are many lists, list 1, list 2, and so on, and there are threads that are accessing these lists. With each list, there is a lock. So there is a lock for this one, lock 1, let's say, and this is lock 2. And because insert only operates on one list, it's okay, just take the list lock corresponding to that list, and then you release it. Similarly, if you want to operate on this list, you take the lock corresponding to this list and release it. In this example, there is no operation which needs to touch both lists, right? Either you insert in this list or you insert in that list. So it's okay, right? But let's so also we saw an example where there was this transfer function which would transfer money from account A to account B. Here I said, okay, let's have a lock per account. So per account lock, right? And here the way you are going to structure your code is you are going to acquire A dot lock, acquire B dot lock, do your operation, and then say release A dot lock and release B dot lock. Right? Because this operation requires touching both these accounts, you have to take both these locks, right? So if I were to draw the picture in memory, so let's say this is memory. These are various accounts, A, B, C, and so on. Each of these has locks LA, LB, LC. So I basically make sure that when I'm touching B, I am holding lock B, right? If I have to make a transfer from B to A, then I should hold both these locks a priori. Initially, I take both these locks, and then after I've taken both these locks, then I can do this transfer, and then I can release both these locks, right? Okay. Similarly, we saw another example where there was sum, which will just sum all the accounts. Here you were going through all the accounts and summing all the money of all the accounts, right? In which case you wanted to touch all the accounts, right? And so, and you wanted to do this computation in an atomic manner. So in this way, what you so that you know the sum is correct at the any day. So what you're going to do is you once again have per account lock. So you're going to say per account lock. Let's say. So then you're going to say acquire what? All locks. So let's say I just say for all accounts A, acquire A dot lock, right? So acquire all the accounts before doing this, right? Then do your computation, and then for all accounts A, release lock. Right? So the invariant is that associate a lock. So let's say there's a memory and there is a lock with this memory, and there's another lock with this memory. And if there is an operation which involves both these things, then take both these locks. Okay. So in the example of our list, we had a lock 1 and lock 2. So we were doing insert. But let's say I had an operation called move. So I took the example of insert, but let's say I had another example with it move, right? Which will delete one element from list and put that element in list 1, right? This operation, if it needs to be atomic, will need to touch both lists, and so you will need to take both locks before doing that operation, right? So this one needs only one lock. This one needs 2 locks, right? Just like transfer needed 2 locks, insert needed 1 lock, sum needed all the locks, right? Okay. All right. So we I hope we understand a little bit about locking. Let me know if there are questions. I'll take a 2-minute break to address questions if there are any. before I move to my next topic. Any questions? Okay. If there are questions, please feel free to interrupt me. All right. So now I'm saying that, so of course, we are talking about, we're trying to make our locking as fine grained as possible, right? If you have had coarse grained locking, you would have just one lock for all the data structures. And so they were having no problem anyways, but that's not a very good design because, you are serializing a lot of computation. Fine grained locks allow many different threads to execute in parallel. All right. But there is a problem of deadlocks as we have seen before, right? So let's say I have an operation which says transfer from account A to account B, right? And I say acquire A dot lock, acquire B dot lock, do something, then release A dot lock, release B dot lock. All right. Now, if two threads called transfer from account X to account Y, and this one says transfer from Y to X, then as we've seen before, there can be a deadlock. Why can there be a deadlock? Well, first thread will acquire a lock for X. Second thread comes in, it acquires lock for Y. Now this thread wants to acquire lock for Y. It will have to wait because lock Y is already acquired. And the second thread will try to acquire lock X, and it will also wait because lock X is always acquired, and none of them will be able to make progress. Right? So let's look at this in full detail. So this transfer XY and transfer YX. So what happens is, let's say this is one thread that's called transfer XY. It basically acquires X lock, tries to acquire Y lock, but before it can acquire it, another thread comes in which was doing transfer YX, right? It acquires Y lock, tries to acquire X lock. This one waits because it just waits because it knows that somebody has acquired Y lock, so it cannot get it. It just keeps waiting, hoping that the other thread will proceed and some later release it. But the other thread is also waiting, right? So this one also waits. And so both threads keep waiting for the other thread to release the lock, but none of them will ever release it because both of them are waiting, right? And so you have a deadlock. Right? In fact, as we discussed last time, because of any cyclic dependency in lock acquisition order, right? So for example, if one thread was doing transfer XY, another thread is doing transfer YZ, and yet another thread is doing transfer ZX, you can still have a deadlock. Right? Okay. So now the question is, how do you prevent a deadlock? Well, the one common way in which operating systems prevent deadlocks is by ordering lock acquisition. Right? So recall that deadlock can occur. Let's say there are multiple locks. Let's say this is L1, L2, L3, and so on. And a deadlock can occur if, let's say I draw all these locks and I draw an edge between two locks. If a thread can hold one lock and then try to acquire another lock, right? So in this case, let's say a lock can be hold a lock from L1 to L2, hold a lock L1 and try to get L2, right? So then there will be an edge drawn like this. Then the second thread can hold lock L2 and request for lock L3. So an edge can be drawn like this. The third thread can hold lock L3 and request for lock L1. And so an edge can be drawn like this, right? And you have a cycle, and which indicates a potential deadlock. Instead, if you say that there is an ordering, which means you will never request a lock. So you order the locks. So instead of this, let's say if I order, so if I put an order and I say L1, L2, L3, and I say a thread will never request a lock, a small, a lock preceding a held lock in a, right? So let's say I make an order and I do a precedence order where L1 precedes L2 and L2 precedes L3. So I have basically made an order, and then I say that I'll ensure that thread will never request a lock preceding a lock that is held, right? So if I'm holding L3, I will never request for L1. Similarly, if I'm holding L2, I can request for L3, but I'll never request for L1, right? So if I ensure this, then what will happen is only edges of forward direction will be allowed, right? So recall that I was drawing edges if I was holding a lock and requesting another lock, because I can only do this for locks which are succeeding me in this order. The edges can only be drawn in forwards, right? And so the reverse edge here will be disallowed, right? So the reverse edge will be disallowed. If you can do that, then you can ensure deadlock freedom. Okay, so let's see how this works in practice. Let's say I have memory, and this is shared region 1, S1, and here's the shared region 2, S2. And let's say this is a lock L1 that's protecting the shared region S1, and here's a lock L2 that's protecting this shared region L2. And let's say ensure that always or never acquire L1 if already holding L2, right? So if you're holding L2, you can never, the programmer should ensure that he'll never try to acquire L1, right? That should be the responsibility of the programmer. If he can ensure that, then L1 will always be acquired before L2 and there will be no deadlock, right? So let's say there was some operation which involved, moving some data from S1 to S2. The programmer should ensure that L1 is acquired before L2. This is allowed, right? And do something and then release L1 and release L2. Right? This is okay. But what's not allowed is that L2 is acquired first and L1 is acquired later. That's not allowed, right? Because that will violate this rule that never acquire L1 if already holding L2. Okay, so just to make sure, acquire L2 followed by acquire L1 is not allowed. Okay, so if I have multiple locks, I basically need to make sure that I need to order them in some way, anyway, and I basically need to impose this invariant or constraint that locks will only be acquired in their strict order. Right? You cannot acquire a lock later which occurs later in the order and then request for a lock that occurs previously in the order. Not allowed. Okay. The question is, how do you order these locks? Well, I said any order is okay, right? Any order. It doesn't matter. So for example, I could just use the address of the lock to decide whether I want to acquire it, in which order I need to acquire it. So one way to do it is, if I'm going to do an operation that involves taking lots of locks. So let's say I was doing the sum operation, right? And the sum operation requires me to take the locks of all the counts. The question is, in which order should I take the locks of all the counts? Well, one option is just take the locks in the order of increasing account number. All right. So, let's say the accounts have a number associated with it. So I'm going to first and then request for a lock of account 5. Not possible. The other way is possible. Right? So if I ensure that ensures that there will be never any cycle in my dependency graph. Right? And so then there will never be a deadlock. Okay. So for example, let's say I had transfer. So in our transfer and sum, right? So these are so where I could say transfer from A to B and sum for all accounts. So let's say one example ordering is order by account number, right? So if I order by account number, I need to make sure that if I want to hold 2 locks, I will always hold the lock of the lesser account number first, right? So for example, now my code will be, let's say it's transfer A to B, then I'll say, now I cannot just say acquire A, acquire B, because if A's account number was greater than B's account number, then my invariant will get violated, right? So I need to check what is A's account number, then I need to check what is B's account number. Whoever is less, I'll account that lock first. So I'm going to say if A dot number is less than B dot number, then acquire A dot lock, acquire B dot lock, else acquire B dot lock first and then acquire A dot lock. And then you will do your computation, whatever it is, right? And then you will release. Right? Notice that release does not need to be ordered, right? You can release in any order. It doesn't matter. Acquires need to be ordered. Okay. All right. If you have any questions, feel free to ask. Let's look at the example of sum. I say sum, all accounts. Here I'm going to take what? I'm going to say, I want to acquire the locks in sorted order of the accounts. So I'll first sort the accounts right? And then for all accounts A in sort accounts, I'm going to say lock A dot or acquire A dot lock. Right? So I've sorted the accounts based on account number. It's important that I sort it, right? Because otherwise there can be a deadlock. Right? So I'm going to acquire the locks of the accounts in a sorted order. And then I'm going to do the computation. It's important to do that in a sorted order to prevent deadlocks. If I don't do it in a sorted order, then there can be deadlocks. Okay. Right. So any questions at this point? All right. In general, figuring out which locks to use and where to put them is a bit of requires very careful reasoning. But we said that we're going to use the simple idea that whenever you're doing an operation which involves multiple shared operations, just take all the locks. So associate one lock for every shared region. Whenever you are doing any operation on that shared region, take its lock. Whenever you're doing operations on multiple shared regions, take all the locks. Also take those locks in a certain order, right? So that's my locking discipline. And if you follow this locking discipline, you will ensure that your program is free from races, which means all sections, critical sections are mutually exclusive. So you don't have, you don't have bad overlapping schedules. And you will also ensure that your program is free from deadlocks, right? So it cannot happen that you're holding one lock and waiting for another, and then yet another thread is holding the lock that you need and waiting for the lock that you're holding, and so you have a cycle and you're waiting forever. So if you obey these principles, you will ensure both race freedom and deadlock freedom. Okay, so let's say let's look at the example of lists, right? So we had in our example we said, I'm going to have a function called insert list and data. All this was very nice. So if there was some code, so let's say there's some function and which is calling something, and he could just say insert list data, and let's say there's another function called delete list data. It just deletes the first element from the list and return, or sorry, not delete list data, just says delete list and returns data. Okay, let's say there are two functions, insert and delete. All right. So there are two functions, insert data into list, and the other function is delete the first element from the list and return the corresponding data. Right. Let's say I wanted to write a function which said move. Right. As I move from list L1 to list L2. Right. Let's say I want to write this function. Well, in a modular way, I could write it in this way. I could just say, and I could just have a local variable which says data, right? And then I say data is equal to delete L1, and I could say insert L2 data. Right? So usually when you are programming, you are you want to keep your code as modular as possible. So you say, oh, this is a function that will insert, this is a function that will delete, and if you want to write a move function, it will just delete from here and insert to here, right? So in a sequential programming environment, this is correct. I just delete one element from here and then insert one element there, right? Whatever was the locking needed to do this operation should ideally be inside, right? So I don't care. I mean, as a client of this these functions, as somebody who wants to execute these functions, insert and delete, I shouldn't need to worry about who is, whether this list needs a lock or not. Multiple threads could be calling this, etc. And so I don't need to worry about whether insert internally is going to take a lock or not in general, right? But if you look at this function and if you look at it, it's actually incorrect, because if multiple threads call move simultaneously, one thread would have deleted. After delete, it would have released the lock, and yet another thread could have deleted again. So there's a race condition between delete and insert, right? At this point, a race condition can happen, right? Because no locks are held here. Right? So if you wanted to make this whole thing atomic, you would want to actually remove, you would want to do something else. You want to say, okay, delete and insert are functions, but I want to do move, which is atomic. So I cannot just call delete and insert. Instead, I need to call delete and insert in a different way. I'll first acquire L1 lock, right? Then acquire L2 lock. I'll have to do this in an ordered way. I'm not showing the order here. Let's say the order is L1 is less than L2, but if it's not, then you need to check who's which is less, and then you're going to say delete. But this time I cannot call the delete, because delete is also going to try to acquire the lock. So I'll have to write a new function which says delete no lock, right? And similarly insert no lock. So these new functions should not be actually taking the lock, because the move function is taking the lock a priori, and the move function needs to take the lock because the whole thing needs to be atomic, right? And so now you need to release L1 lock and release L2 lock, right? So what has happened is these functions insert and delete. Could you please focus here? Yeah. So what has happened is these functions insert and delete cannot be used in a modular fashion anymore, right? If you want to write another function which requires operations on two different lists, then it needs to be written differently. Just call these functions modularly, right? And I had to define new functions, delete no lock and insert no lock, which will not acquire the locks, which will assume that the lock has already been taken, and instead acquire the locks before and after both these operations. Plus, I will need to ensure that these are ordered, right? So in general, locking basically makes your code less modular, right? So locking locking kills modularity, you can say. Or hampers modularity. Right? So code that was modular has to become immodular, and the callers need to be aware of what locks these functions are going to take, and actually take them themselves, and not just take them themselves, they also need to do it in an ordered manner. And so the caller, and this keeps propagating to the callers, because all the callers, if the caller is going to operate on multiple shared regions, and it knows that all these shared regions will take locks, then the caller itself needs to take those locks, right? He cannot just rely on these individual functions to take those locks. So it would have been nice if I've written this code such that I don't have to worry about locking. The locking is internal to delete and locking is internal to insert. But unfortunately, that's not possible. I need to take the locks myself if I'm doing operations on multiple objects. All right. So any questions at this stage? We have discussed many important things actually, and it's very important that you understand this. I received an email from one or two students saying that is there any textbook for the material I am teaching? Well, I will search for this material in the different textbooks, and I'll send your instructor a link. So if your instructor has sent me an email before, I'll be able to send him or her the link to the book. Also, I'm planning to prepare some notes which I'll share with you with this material. Okay. All right. Okay. All right. So let's take another example. So now, if assuming that because there have been no question, I'll just assume everybody's understanding everything, and so I will now ask you questions. All right. Okay. So let's see. All right. So let's say there is some code which so let's say there are some shared counters. Let's say I define a counter, struct counter, okay, and each counter has two fields. Firstly, its count, and the other is whether it has been allocated or not. So let's say I define a struct counter, and I define a global variable, a shared variable which says struct counter, and these are counters. Let's say I have 100 counters. Okay, so I have 100 counters initially. Okay, and let's say initially all these counters have their allocated flag set to 0. Right? Okay. So now let's say there are multiple threads, and there's a function called increment. Okay. And increment takes a counter and just as counter dot count plus plus. Okay. So multiple threads can call increment simultaneously, right? So I have 100 counters. A thread could call increment on one of these counters, and it could increment the count of that counter. My question is, if multiple threads can call increment simultaneously, is this code correct? If not, then what would you do to make it correct? Would you add locks? If you would add locks, how many locks will you add? Okay, and where will you put calls to the acquire and release functions in this code? All right, very simple questions. Let's see who answers them. All right, so how many locks? Where will you put the acquire and release to make this correct? So firstly, how many locks would you use? Okay, there's a question from SVEC. The question is, let's say one thread holds a lock on X and another thread is trying to acquire that lock, the first thread doesn't release the lock, then what happens? The other thread will keep waiting forever, right? Yes, I mean, but both these threads have been written by the same programmer and they should be mutually trusting each other, right? So if the programmer has basically one thread is not releasing the lock, it's a bad program. So all the other threads will suffer, right? So the programmer should ensure that a lock which is acquired is also released in due time. Oh, okay, right. So there is a thank you. So there's a hint from the LNMI. HTTP counter dot count plus plus. All right. Now my question is, how many locks do I need? And where should I put calls to acquire and release? Could you please focus on this? How many locks do I need? Multiple threads can call increment. How many locks do I need? Okay, okay, VCE, please say.
Should we require 2 locks, one for acquiring and another for releasing?
I think your microphone is not working.
Hello? Yeah. One lock for acquiring, another lock for releasing. 2 functions. Is it audible now? Is it audible, sir?
Cannot hear you. I think there's some problem.
Is it
There's
audible
some
now?
problem at our end. Okay, yeah, I can hear you now. Please say, sorry. Yeah, tell me, VCE? I cannot hear them again. VCE, could you please try speaking again?
Hello?
Yes,
Hello?
yes, I can hear you.
Can you hear, sir?
Yes, I can.
So we require 2 locks.
2 locks.
One lock for acquiring, one. Yeah, 2 locks. One for acquiring and one other for releasing.
Oh no.
Hello?
No, that's wrong. You acquire and release the same lock, right? You don't acquire one lock and release the other lock. So that's wrong. Anybody else from VC?
Sir, you place condition, right? Before that condition, you have to acquire the lock.
Okay, good. And when do I release the lock? After at the end of the function. Okay, but how many locks do I need? Only one lock for all the counters? For all the counters?
For each counter, one lock, sir.
Okay, for each counter, one lock. How many counters are there?
100 counters, sir.
So how many locks do I need?
100 locks.
Okay, I need 100 locks. Okay, good. Thank you. All right, so we need 100 locks. There are other answers here. Let's see. Okay, PECUT says one lock. Well, actually, the answer is I could either use one global lock or I could use 100 per counter locks, right? If I use one global lock, that's coarse grained locking. If I use 100 locks, that's fine grained locking, right? So let's say I use 100 locks, right? So let's say I have struct lock locks 100. One lock per counter. In fact, instead of doing struct lock locks 100, I can probably do just this inside the counter field, have a lock also. Okay. So every counter has also a lock. So that basically means there will be, if there are 100 counters, there will be 100 locks. If there are 1000 counters, then there will be 1000 locks, right? Because I have put the lock inside the structure counter itself. Yeah, please focus on this. Okay. So if I do this, then what I'm going to do, I'm going to say, okay, let's see, I'm going to add lock. So I'm going to say acquire counter.lock, and I'm going to here say release counter.lock. Okay, that's fine grained locking. If I had used coarse grained locking, then I would have had just global lock. Instead of doing acquire counter.lock, I would have done acquire global lock. Okay, all right. So that's increment. But let's say simultaneously there's another function. So that was increment. Right? Let's say there's another function called, so there's increment, and let's say there's another function which says get counter. Right? And so here what I'm going to do is I'm just going to say return counter dot count. Right? I'm going to say if counter dot allocated return counter dot count, else let's say return -1. Right? So let's say this is my code. Okay. So what locks will I use here? We maximize this. So what locks will I use here? Well, once again, I have a per counter lock. So once again, what I could do is I could put acquire lock here. Right? Where do I release? Where should I release the lock? Okay, so somebody answer me. Where do I release? Where should I put release? Before return statement. Okay, so there's an answer from PECUT. Thank you, PECUT. You say it's before a return statement. Yes, initially allocated is all 0, right? So all things are allocated, but we're going to have more functions which are going to set allocated to 1. But let's say it's 0. So where will you put release? He says before the return statement. But is it okay to put the lock before the return statement, because you're going to, after that, if you put a release there, after that you're still accessing the shared variable count, right? So it's not okay to just put release before the return statement. Perhaps the better thing to do here is, let me write it on a different sheet so that I have more space. So let's say void get counter I said if counter dot allocated is equal to 1, then return. So instead of return, what I'm going to do is I'm going to have a local variable int L count, local count is equal to counter dot count. Then I'm going to say return L count. And here I'm going to say else return -1. And let's put the locks. I'm going to say acquire counter dot lock and release counter dot lock and release counter dot lock. So the thing that I've done differently now is that the read of the count variable which was shared I've done before releasing the lock. So I have read this into a local variable. This is a local variable, not shared. After that I've released the lock and then I'm returning the local variable. Right? So if it's not enough to just say release counter.lock before return counter.count, right? Because counter.count itself is shared. And you want to make sure that all accesses to this variable are also protected by the lock. Right? The better thing to do is to read the shared variable into a local variable and then release the lock and then return the local variable's value. Right? So basically what I have done is I want to make sure that whenever I touch a shared variable, the lock is held, right? So, but because I wanted to return the value of the shared variable, I instead read it into a local variable while holding the lock, and then I release the lock, and then I'm not going to touch that shared variable, right? Then I'm just going to return the local variable. So I can do that. Okay. All right. Let's stop here, and I'll continue our discussion next time. And we'll also discuss. We have looked at one type of synchronization called locks. We'll also discuss more types of synchronizations like semaphores next time. Okay. All right. Thank you.